Good afternoon. We have looked at the folded cascode opamp. What it offers is a higher output signal swing because of two things. One is, there are two transistors to the top and the bottom, and also the earlier either the simple differential pair or the telescopic cascode opamp, the output was taken from, it was connected to the input transistor in some way. Okay, so the input voltage and the output swing limit were connected. Now it is not. You can see that these two transistors are isolated from the output. So the output swing is not dependent on the input common mode voltage. Whereas earlier in the simple differential pair or the telescopic cascode, the input common mode also introduces some constraints to the output swing. Okay. So that way this offers a higher output swing, and that's the main use of it. Of course, the penalty is because of this additional bias source, you get extra offset, extra noise, and so on. Okay. And also the output impedance is probably going to be lower than that of the telescopic cascode. Of course, that depends on the transistor sizes, but for similar lengths, it is going to be lower. Okay. So any questions about the folded cascode or the associated calculations? Now I just took the output branch here, right? And then ask you to calculate what the output current would be in this case. So what will be the output current? So first of all, this the upper delta IA, the way I have it, so it goes through this, okay, and then it gets mirrored out, right? And then this one comes out that way. Okay, so the two together will give you 2 delta IA. Okay, and here what happens to this? This is straightforward. This goes out. It goes out like that. What happens to the other one? Where does this flow? This delta IB, where does it flow? This delta IB. So it is being injected to this common node between M7 and M3. So where does this flow? Into M7, M3, M7. Why? Is it? Let's take that separately. So I'll just show a constant current from the top, because when the other signals are not there, it is just a constant current source from the top. Okay, and I have delta IB here. Okay, and this is some fixed bias. Okay, what is the impedance looking up? Impedance looking up that way. What is it? What is it? What were you saying? What is the impedance looking up? What is it? High. How high? Very. When I draw something like this, let's assume that this is an ideal current source, right? It is infinity, because clearly this fixed current is flowing through this, and you cannot change that current no matter what. Okay, so that means looking up, it will be infinity. So where does this current flow? Through M3. Okay, so it flows into M3. What really happens is, again, if you assume that there is some parasitic capacitor here, and let's say you apply a delta IB as a step. Okay, now of course, for a step input, you can just around the transition, you can assume the cap to be a short. It will flow through M7, but then it will flow into the capacitor and raise this voltage. Okay, and this increased voltage will make a current flow through M3. So eventually, in steady state, a DC delta IB will just flow through M3. Okay, now this looks slightly unfamiliar, but if I had this without the cascode, what would happen? Where would it flow? Through M3, obviously, right? And this gate voltage would be delta IB by GM3. That is true in both cases. Okay, this is again feedback. This feedback goes through this transistor. Eventually, you will have a voltage delta IB by GM3 at the gate of M3 and delta IB current through M3. Okay, so that's true whether you have a cascode or not. The feedback is completed through the cascode. Is this okay? So this kind of thing you have to be a little careful. So when you see something like this, yes, the impedance is 1 by GM. You are almost trained to automatically say this. But this is true only if, now let's introduce some impedance here. Okay. If you evaluate it along with this RDS, right, you will get some expression that also includes RD. When RD is somewhat small, then it doesn't matter. This will be very close to 1 by GM. But very clearly, when RD is infinity, this cannot give you 1 by GM, right? Because no incremental current can flow there. It's an open circuit. Okay. So that is something you may have to be careful about in some cases. So anyway, so what happens to this delta IB? It flows here. So that creates a voltage delta IB by GM, which in turn causes a current delta IB, which flows there. Okay. So the output will be 2 delta IA plus or minus, minus. In this case, it is minus. Okay. So the point is whether you inject the currents differentially to these nodes. This was more intuitive in that way. These were just common gate amplifiers for the differential pair. But you can connect them to these nodes also, and it works in exactly the same way. Okay. So you can connect them either there, which is a more natural sort of cascode like thing, or here into the current mirror nodes. It works in the same way. Okay. Any questions? So why did I bring this up? What is the point of the circuit? No, the circuit, no. The noise from M9 and M10 will come through exactly the same as before. That part has not changed at all, right? What were you saying? You have? Okay. Yeah. So one of the, so the differential pair, right? If you have an NMOS differential pair, okay. So then this VICM, especially the lower limit is somewhat high. It has to accommodate VDs at 0 at a current of 2I0 plus VGS of M1. Okay. So you have to leave quite a bit of room from 0 volts, from ground. Okay, you cannot go very close to 0, right? And then if you have a PMOS differential pair, the opposite happens. So for this, I'll just put a subscript P. It has to be less than VDD minus VDSAT. I'll call it 0P at a current of 2 I naught P minus VGS 1P at a current of I naught. Let's say the currents are the same, so I'll just still call it I naught. So this is 2 I naught and 2 I naught, M0P, M1P, M2P. Okay. Whereas on the other side, like the NMOS transistor, you can take the input common mode to a pretty high value. And in the PMOS common mode, you can get PMOS differential pair, you can take the common mode to a pretty low value, close to 0 also, or maybe even below 0. Okay. So now sometimes this may be a requirement, that is, especially if you have a non-inverting unity gain buffer like this. Okay. So now in this case, the input common mode is the input itself, right? I mean, ideally V naught equals Vi, and the input common mode is the average of the two. It is the input voltage itself, and the output is also equal to the input. So now what happens is that every signal has to obey the corresponding swing limit. Okay, so the output should be between the maximum and minimum limits. Also, the input common mode, which is the same as the input or output, okay, should be between its maximum and minimum limits. Okay. So the swing limit of this circuit, as we saw, we can make, in fact, when we come to two stages, we'll see, we can make the output swing pretty large. That is, you can make the output state such that you have only one transistor towards the top and one transistor towards the bottom. I think I have mentioned this before. The best kind of swing limit that you get is typically when the output is connected like that. Okay. So you have to accommodate only one transistor at the bottom and one transistor at the top. Okay. So the output swing can be, it will be sort of symmetrical. You have to leave some room at the top and the bottom. You cannot go all the way to the rails, but you can go pretty close to the rails. But then the input common mode limit, it looks something like this. Okay. So obviously you cannot have this signal within those limits. Okay. So the swing limit would be limited by that one. Okay. Swing limit would be limited by the input common mode. So in such cases, it is useful to have an op-amp whose input common mode range extends over the entire range. Okay, it's not asymmetrical like this. And that is where this kind of stage may be useful. So what you do is, you have this folding stage that we use for the folded cascode. Okay, and then you can connect the other way around to get the right polarity. Okay, you can connect that there, and you can connect the other one. These are connected together actually. These two are, they receive the same input, which is the input of the op-amp. Both differential pairs are connected to the same inputs. Okay. And then you take the output from over there. Okay. So if you have VICM plus VD by 2, VICM minus VD by 2, we will have currents which are increment. I will show only the incremental currents. This will be plus GMN VD by 2, and this will be in the other polarity GMN VD by 2. Similarly, on the other side, this will be GMP VD by 2 and GMP VD by 2. And if you terminate the output in a incremental short circuit, you will get GMN plus GMP times VID. Okay. So you get the sum of these two, right? But what happens now is that the NMOS differential pair for very low input common mode voltages, it just turns off because this voltage becomes too small, and then that's it. The currents become very small, and that's the end of it. But the PMOS is still active. Similarly, for very high input common mode voltages, the PMOS turns off and the NMOS is still active. Overall, the op-amp is active throughout the range. In fact, the input common mode range, it can even be higher than the supply rails a little bit on either side. That depends on the exact values of VT and so on. But at least it's not asymmetrical like when you have only a single differential pair. Okay. So this is called rail to rail input op-amp. So that folding structure helps you to add these two currents, okay, so that one is not completely turned off. Is this clear? Is the principle behind this? Is this okay? So now if you make a circuit like this, one or the other differential pairs will be active throughout the range. So the output voltage will be limited by the output swing limit, not by the input common mode swing limit. Okay. Is this fine? Do you see any problems with this op-amp? Huh? Yeah. Correct. Both of them will be active. So what is the issue with that? Yeah. So now the GM is dependent on the input common mode voltage, right? It will be GMN only when the input common mode voltage is very high, GMP only when the input common mode voltage is very low, and GMP plus GMN when the input common mode is somewhere in the middle. So that way this has, and similarly, if you think of this small signal unity gain frequency, that will be different. It's a function of the input common mode voltage. So those complications are there, and people have tried to come up with fancy ways of deriving these tail currents, so that you can make the tail current itself dependent on the input common mode, so that the GM remains more or less constant. Okay, so that is one of the problems. GM is dependent on the input common mode voltage. Okay, and also another problem is, as you know, the input referred offset is, of course, the mismatch between M1 and M2, the mismatch between the input pair transistors directly contributes to the input referred offset. Now, there is no reason to expect that the random offset of this differential pair and that differential pair are the same. They'll be definitely different from each other. Okay. So that is why this circuit is not suitable for very low distortion or high precision applications, because let's forget about this GM variation and so on. So So let's say there is an input referred offset VOS. What happens now? If the input is like that, the output will be shifted by VOS. Let's throughout that. Now what happens is you expect VOS for the lower common mode voltage. So that could be different. So let's say that is something like this. Okay. So now, of course, the transition between these two will be smooth, but you can expect an output that has some shape like this. Here it is following this VOS, and then it jumps, and then it follows that VOS. And so the output is visibly non-sinusoidal, right? It has deviated from being sinusoidal. So it will have a substantial distortion because of this crossover. Okay. That is, when the PMOS pair is active, it is giving you VI plus VOSP. When the NMOS pair is active, it will give you VI plus VOSN. These two are different from each other. So even if everything else is ideal, even if the gain is very large so that the output nearly follows the input, you will get input plus something in a part of the cycle and input plus something else in another part of the cycle. So the output is clearly going to be non-sinusoidal, right? So which gives you distortion. But the virtue of this is that you have some structure that works with a variable common mode. Sometimes this offset may not matter and you may not be operating with sinusoidal signals. It could just be that the input common mode can vary a lot. So in such cases, this is useful. Okay. Any questions here? What is that? Input common mode limit. Yeah. Input common mode limit is wider than any of the other circuits. No, this is VI of this VI and VO of this circuit. No, common mode is whatever it is, right? I mean, it is VI itself. You don't apply an input to the op-amp directly, right? It is whatever comes from the circuit. In this particular case, assuming that VO is exactly equal to VI, the input common mode is the input voltage itself. Okay. So that means that over this part of the cycle, NMOS is active and over here PMOS is active. Okay. Of course, there will be some region where both are active. Is that okay? Okay. Just a second. So if you plot the GM of this op-amp versus VICM, here I mean the total GM, not that of any individual transistors. At low levels, it will be GMP, and somewhere in the middle, it could be GMP plus GMN, and at higher levels, it is GMN. Okay. Vary the input common mode voltage from 0 to VDD. This is what is likely to happen. If you modulate the tail current with the input common mode voltage, you can try to keep this constant. But even then, I mean, the offset problem will not go away. So the offset is also a function of the input common mode voltage. So essentially it can change in some way. This is random offset. So it will change in some way with here it is dominated by PMOS and here you have both and here it is dominated by NMOS. Yeah. No, I mean, there are ways of using both NMOS and PMOS, but this is not really giving you any advantage, right? That is, you have both NMOS and PMOS, but you are burning separate bias currents in each of them. If I had a bigger differential pair with a higher current, you would also get more GM. So that way there is no advantage in this. There will be an advantage if the bias current is shared between the NMOS and PMOS transistors and you are somehow able to add their GMs. So that way for the same bias current, you get GM1 and GMP both. But this circuit is not that. This is anyway using two different bias currents. Instead of adding GM, to get higher GM, I won't even do this if that's the only goal. I would just put a bigger differential pair here. Any questions about this? So once you have the circuit building blocks, you can keep making new circuits. Okay, so that's why it's also very important to understand the building blocks very well. Yes. No, because everything changes in a continuous way, right? See, earlier, I mean, you know that if you have only N, the offset will be the offset due to this plus some contribution from these as well. And here, the offset will be due to this plus some contribution from the same parts. Okay. So essentially, it will be the expression for the offset could be that offset variance, right? So this here in the middle, both NMOS and PMOS pairs will be active. Okay. So this will contribute to some part of the offset, that will contribute to some other part of the offset. So one way to think about it also is that so let's say you tie the input to 0, okay, and then you look at the output current that is there. That is the offset, right? And that divided by GM will be the input referred offset. So now as you change the input common mode voltage, there will be some at very low input common mode voltages, there will be no contribution from this, only from that. Now in the intermediate values, there will be some weighted contribution from these two, right? And as you go to very high input common mode voltage, there will be contribution only from that. So it's sort of completely, I mean, it changes from being only from N to only from P to only from N. Anything else? So now we understand single stage op amps pretty well. I mean, if you make a differential pair with a current mirror load, you have a single stage op amp. The disadvantage is relatively low output resistance and consequently low gain, right? So we can improve the gain by using cascode, either telescopic or folding. You choose which you want based on the swing and noise and so on. Okay. Now the other types of stages that we saw were, I mean, other type of op amps that we saw were these multi-stage op amps. Okay. So where essentially we tried to improve the integrator. This gave us like 2 and 3 stage Miller compensated op amps. There were also feed forward op amps. I will discuss them only after we come to fully differential op amps, because typically, in fact, we'll move to, after the 2-stage op amp, we'll move to the fully differential op amps. Fully differential is what you do in most cases on an IC. Okay. And the feed forward op amps are typically used only on ICs. You don't make them with discrete components anyhow. So it is possible, but anyway, I won't spend time on that. So I will discuss only the Miller type multi-stage op amps. Okay, in the single-ended version. Single-ended op amp means the input is always differential, but the output is just 1 voltage with respect to ground. Fully differential means you will have again 2 output lines. Each should be the opposite of the other. Any questions about single stage op amps? Two-stage op amp. Now, this is what we have, right? Okay, and of course, we expect that there will be parasitic capacitors here and there. So how would we go about building it? What stage would we use for, or what circuit would we use to implement GM1? Fully differential op amp. Why? It's not fully differential at all, right? Differential pair. Basically, whatever single stage op amp we have used so far can be used in place of GM1. Okay, any of them, the simple stage or the telescopic cascode or the folded cascode or the rail to rail. Okay, all of them are similar in that they have two input nodes. It basically senses the difference voltage between those two input nodes. Okay, so every single stage op amp we have discussed so far, any of them can be used, and you use them based on your requirement. Okay, while drawing, I will draw only the simple single stage op amp. So let me again continue with the NMOS differential pair, just for the sake of familiarity. But of course, don't get confused if you see a PMOS differential pair. Okay, this is GM1. What would you use for GM2? What should you use for GM2? So it has a single-ended input and a single-ended output. So what should I use for GM2? And of course, I still want to get high gain from that if possible. So I would use a common source amplifier with active load, right? So this would be okay. Now I could use NMOS common source amplifier or a PMOS common source amplifier. Which one would I use here? Which one should I use? Should I use an NMOS common source amplifier or a PMOS common source amplifier? Why? So you expect that so the sort of natural bias point here, which is VDD minus VSG of this transistor, that is closer to VDD. Okay. Now, of course, with very low supply voltages, these things may not be all that true, but definitely with a relatively generous supply voltage, this will be true. So it makes sense to use a PMOS common source amplifier after this. But of course, you actually do see circuits in which you do have an NMOS common source amplifier. Okay, is that fine? So we will use a PMOS common source amplifier. I hope the reasoning is clear. Whenever you connect stages, right, you have to make sure that each stage has the right operating point. Now, one way to do it in discrete circuits is you use AC coupling everywhere. That is, then you bias each stage independently. You don't worry about the operating point of one affecting the operating point of the other. But of course, that doesn't work for every case. And inside an op-amp, you don't want to do AC coupling because you want this to work also for DC. So if you have to DC couple circuits, basically the operating point of the output operating point of one stage should be compatible with the input operating point of the following stage. Okay. Because of that reason, it makes sense to use a PMOS common source amplifier after this. Okay. And I'm showing it like this. It's assumed that these are biased from the same current mirror with appropriate size ratio. Okay. I'll call this M11 and M12. Okay. Which is the positive input terminal of the op-amp? Gate of which transistor is the positive input terminal of the op-amp? M1, M2. Which one? Which is the positive input terminal? How do you find out? So basically, you can always imagine that if the gate swings, the drain swings in the opposite direction. The gain from the gate to drain, the gain from gate to drain is negative. It is the common source amplifier's gain. The gain from source to drain would be positive. Not relevant here, but if you have another circuit in which you want to determine the signs quickly. So you can see you have one inversion there and another inversion over there. Okay, so this is the plus terminal of the op-amp and this is the negative terminal of the op-amp. Okay, and anyway, that is evident from this as well. You feed the input to negative terminal of this GM, and that's actually the plus terminal of the op-amp. Okay, the second stage is inverting, and then we need to stabilize it. We have to have this capacitor CC, right? Or to make an integrator, you need to have this capacitor CC. Okay. So first we can map the parameters of the op-amp to the circuit parameters here. What is this GM1 in terms of the circuit values? What is the GM1? It is the GM of the differential pair. Okay. Okay. And of course, you expect to have some output resistance here. So what is that? RO1. What will that be? What will that be? Yeah, basically it is the output resistance of the differential pair, which using my usual notation, I'll write it as RDS1 parallel RDS3. What is GM2? What is GM2? It is GM of M11. Okay. And what is RO2? Again, you expect some finite output resistance over there. What is that? What is it? RDS11. Okay. Now, what will be this parasitic capacitor C1? Where is the C1? At the input of the second stage. So what will be that? So you have how many transistors? Basically, you see everything that's connected there. That's all, right? What all are connected there? M2, M4, and M11. M2 and M4 will contribute their CDB. M11 will contribute its CGS. Okay. Right? What about this capacitor C2? Keep in mind that you could have some load connected to the. So let me add that to both. So this op-amp in its application could be driving some load like this, RL and CL. Okay. So what will this change? What will RL change? So if you assume that RO2 is the RO2, if it's the output resistance, this is what it is. To calculate the gain, you will have RO2 parallel RL for the DC gain, right? And if you have a load capacitance CL, this total C2 would be what? CDB11 plus CDB12 plus CL. Okay. Whether you think of CL as part of the op-amp or you add it to the output capacitance of the op-amp is up to you. But basically, transfer function. No. Okay. So basically, we know what because we have analyzed this to death. So we know the transfer function of this op-amp, right? What is the unity gain frequency? What's the unity gain frequency of the op-amp by itself? Again, what matters in a feedback loop is the unity loop gain frequency. But what's the unity gain frequency here? Yeah, this is basically GM1 by CC. I think I just called it CC now. So which is GM1 by CC. Where is the right half plane 0? What is the frequency of the right half plane 0? It is basically GM2 by CC, which is GM11 by CC. And where is the non-dominant pole? P2. What is the primary conductance contribution that appears in the expression? Please go back and revise all this if you're not familiar, because we have done this enough at the control source level. What is the P2 will be of the form of some conductance by some capacitance. Okay, so what is the conductance part? GM2. It's a fraction of GM2 because you have this voltage division between CC and C1. Okay. Plus you also have whatever output conductance is there, including the load conductance. And what is the capacitor? You have CL, which is directly connected there, plus the series combination of CC and C1. Okay. So that's basically all that is there to the two-stage op-amp. You follow the single-stage op-amp with a common source amplifier with an active load, and you have the two-stage op-amp. And because we have good understanding of this op-amp at the control source level, we can now, if you want a certain unity gain frequency with a certain load capacitance, which is typically what you will be asked to do, right? You'll be asked to drive a certain capacitance, certain load, could be CL or could be CL plus RL, with a certain bandwidth. From there, you have to go and decide the specs. Okay. So if you have to have a certain bandwidth, you should have the unity loop gain frequency of that value, right? If you have to have that unity loop gain frequency, the non-dominant pole has to be some number beyond that, some multiple of that. So the non-dominant pole tells you how much GM2 you may have to use. Okay. And then from that you can calculate GM1 and CC and so on, and then you iterate through these values, which I think you've already done in the. You did the two-stage op-amp or the single-stage op-amp in the previous assignment? Two-stage op-amp. So I think that's basically it. We'll discuss some more details of this and then move on to fully differential op-amps. Any questions? Okay then, see you all.